Welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic, an overview of copper properties and the impact on microwave and millimeter wave PCB performance. Now here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation, and I am a technical marketing manager. Today I'm going to be talking about copper foils used in the printed circuit board industry and many of the properties that are critical to understand for good circuit simulations. And to begin with, I'm really just going to be touching on this topic. It's a very deep topic, and if you want more information, I would suggest going to our Rogers Technology Support Hub, and there you can find much more information on this topic. And at the end of this video, there will be a URL shown for you to be able to get to the hub. Now with that, let's go ahead and get started. Shown here is a simplified process for making ED copper. ED is electrodeposited copper. And as you can see, it's a very simple electrolytic plating process where you have cathode, anode, and some metal solution, in this case copper. And essentially what you're doing is plating copper onto a very slowly rotating titanium drum. And depending on the speed, that's how thick the copper foil will be. And then it's peeled off essentially at the end. And there's also a treatment that is applied. And I have not shown that in this diagram here, but that treatment's pretty important. And I'll talk about that a little later. Here is shown a very simplified process again for making rolled copper. And in the case of rolled copper, you start off with a copper billet, basically a very thick chunk of copper, and you go through a series of reducing rolls to get the thickness of the copper that you need. So once you have the thickness, it's rolled up on the end, and that's the very basic process for making rolled copper. Copper surface roughness can impact insertion loss of a circuit and phase response for that matter. The copper surface roughness that I'm talking about specifically is at the substrate copper interfaces as we make the laminate. Now there's a lot of different ways to measure copper surface roughness, and what we do is we use a non-contact laser profilometer. Actually we have two different types. And what we're looking for is some of the surface roughness measurements such as R sub A, R sub T, R sub Z, R sub Q. And I'm not really going to go in detail of those, but I will tell you that R sub Q or S sub Q, depending on how it's measured, is the root mean square roughness of the copper foil. And for some electromagnetic modeling software, the RMS or R sub Q or S sub Q are the values that you want to use. Now there's other software that will be looking for other parameters, and I'll talk about that as we move along here. Shown here are pictures of four different types of copper, and this is top view looking straight down on the surface, and this is the treated surface, and this is a surface that is applied after copper is made. And that treatment's for a variety of things. Thermal stability is one of them, and also bonding, and good for ensuring not having chemical attack and different items like that. Now the treatment also gives some nodulation or some roughness to it, and you can see in the pictures here that the roughness values are given. All these roughness values are in RMS or R sub Q, and the bottom right is rolled copper, and you can see that is the smoothest at 0.35 microns RMS. And you can also see there's a directionality to it. There's a grain direction, and that's due to the way that rolled copper is made. The other three coppers are different versions of ED, electrodeposited copper, and you can see they have different roughness and different surface morphology. Shown here is a top view of the copper being measured. In this case, it's the ED copper that was shown on the previous graphic. And you can see that in a small area that there's pretty significant differences in peaks and valleys. The peaks being the red, the valleys being the dark blue. And that's common for just about any copper, but essentially the rougher the copper surface is, the more variation you get. And in the case of rolled copper, it's very smooth. The picture would look quite different, and you would see much less difference in the peaks and valleys, but still you are going to have some differences in small areas for the copper surface roughness. That's just to be expected. Shown here is a comparison in insertion loss. Y-axis is loss in dB per inch, testing microstrip transmission lines with differential length method. And each one of these curves are the same circuit design, and actually the exact same material is using 5mm RO3003 material. And in this case, we use the same lot of material to minimize any material differences. And the only difference here is really due to the copper type. And we have four different copper types, and in the table of information here, you can see the roughness that was measured on each one of them. And you can also see that the trend of insertion loss corresponds very well to the trend of the copper surface roughness. Again, the surface roughness we're talking about is at the substrate copper interfaces, and these are microstrip circuits. There are several different models that are used in the industry for the electromagnetic modeling software to account for the effects of copper surface roughness on RF performance. Specifically, copper surface roughness will cause increased insertion loss with increased roughness. And also the phase response of the circuit can be impacted as well, where rougher copper will cause a slower wave, phase velocity will slow down, and actually will have an increased phase angle. Now, these models that do this modification of the conductor losses are based on several different concepts, and one of them uses, actually several of them use RMS, root mean squared, which I've already talked about some. And then other models will use SAI, surface area index, and it's also known as surface area ratio. And this is basically a measurement of the surface area of the object that you're testing. In this case, it would be copper foil, and compare that to an ideal flat surface in the same area. So it's really a difference between a perfectly flat surface and the copper roughness that's being measured. Shown here is a chart that's on the y-axis is insertion loss in dB per inch. This is from testing microstrip transmission lines, and specifically the insertion loss at 77 gigahertz. And on the x-axis we're showing surface area index, SAI. And you can see there's a pretty good correlation between the surface area index and the insertion loss, where SAI, surface area index, if it's 1, that would be a perfectly flat surface, and as the numbers increase, that's rougher surface as you increase the numbers. And you can see the insertion loss responds to that quite well. So the correlation between SAI and insertion loss is valid, and there are some models that use this copper roughness relationship to basically add to the conductor loss as it makes sense for the copper roughness. In this video, I'm mostly focused on how to make the copper and also copper surface roughness. There's many other aspects of copper that are important to understand, such as how the copper actually affects wire bonding, the wire bonding process, and there are other things to consider as well. Now, besides the copper roughness affecting insertion loss, it also affects phase response and phase velocity, which I already mentioned, and it can have an effect on group delay and impedance. There's several things. So again, if you want more information on this topic, I would refer you to our Rogers Technology Support Hub, and at the end of this video you will have a URL that will direct you to that website. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.